So today we look at the preamplifier of my homebrew shortwave transceiver, and you see here a picture of it. And we already discussed in a few other YouTube videos. We already looked at the antenna amplifier over here, at the bandpass filters. We did look at the crystal filter and the mixers here and how mixers work. What is still open is this microphone amplifier and two-tone generator. Still missing is this digital part, missing is the amplifier, and today we are looking at this preamplifier. So from one of those mixers we get an output signal, and with this output signal we have to drive the power amplifier, and the signal is way too low and not enough energy to really fully use this amplifier here. So we need a preamp. So this is the circuit of the preamplifier. We have the input here coming from the mixer. We have the common emitter stage, which is generating all the power that we need to get into the amplifier. We have a 12-volt power supply. And we have in between the mixer and the 2219, we have this common collector transistor, which is nothing else but converting impedances. It has a very high input impedance and a very low output impedance. So this output impedance is very nice to drive than the common emitter. And this very high input impedance gives me the guarantees that we don't load the output of the mixer at all. Of course, everything is decoupled with capacities. This is decoupled inductively here. And we set the 2N3904 somewhere in the middle of rail voltage. So that's roughly 6 volt. Then we have a voltage drop between base and emitter of about 0.7 volt. So we are here at about 4.9 volts. And so that's pretty much in the center between 12 volts and ground. And then here we set the emitter voltage to about 2 volts. That gives us a very good and a very nice swing over the impedance here. And in other words, because we have 0.7 volts here as well, we have about 2.9 volts at the base. So that's the circuit. Now a quick view on the circuit. You see the 2N3904, the 2N2219. This is the input signal here, and the output, and it's terminated in a 50 ohm load. And you see also the decoupling capacitors and the impedance matching transformer that we saw before, the schematics. And then that's about it. Let's quickly take a look at some simulation results. I simulated a circuit in LT-SPICE. Here the first diagram shows the input and output voltages. The mixer specification says ±1 volt peak on the output into 50 ohm. So I said, okay, I take 2 volts peak as input. That's the green curve, and the blue curve is the output. And the output swing is almost 10 volt, 9.6 volt peak, and that's about 14 dB amplification. When we look at the frequency response, we start here at 1 megahertz. That's about 1. And we go all the way up to, I think it was 14 megahertz, the 20 meter band. So it's pretty flat, drops off a little bit on the low side, around 1 megahertz. And I didn't simulate any parasitics, any inductivities and stray capacities. And this simulation was done also with an ideal transformer, but of course these transformers are not ideal at all. So I expect a little drop off here at higher frequencies than on the bench. And the third diagram just shows you the currents. The one is the emitter current, the green one. That's the emitter current of the 3904, and that's the collector current of the 2219. And you see at 12 volts we already drive it at 0.7 watts, so that's a lot of power dissipation that you have to take into account. A quick recap on these different transistor configurations. The BJTs have three main and most common used configurations: common base, common emitter, and common collector. What we use is a common collector as a first stage because of very high input impedance and a very low output impedance. So this is typically, it has a low voltage gain. It's about the voltage gain of 1, and it's actually an impedance converter, and you use this transistors configuration mainly for that. The common emitter, that's what you mainly use as power amplifiers whenever you need to amplify power, audio power, HF power. That's the amplifier you take and the most common used. And you have a high voltage gain and a high current gain that results into a high power gain. And the input impedance is not too bad, but not too high. It's moderate. And the output impedance is, they say 50K, could be something between a few Ks to 100K. And a common base is well known as a circuit with a very high output impedance, very low input impedance, moderate power gain, but it's often used in high frequency, low signal applications like maybe antenna amplifiers and stuff like that. You don't see that so much. So we have to take a little bit of a closer look at these mixers. I'm using an 8831 mixer, and this is the output of the mixer, and that just goes to the preamp. And this output is capable of driving plus minus 1 volt peak into a 50 ohm load, and the output stage is given by an operational amplifier. These operational amplifiers, typically an ideal operational amplifier, has an infinite input impedance and an output impedance of 0. The output impedances of an operational amplifier are usually very, very low. However, we hardly have any power available here, so that's why I did choose to go with a common collector circuit first before we go to the common emitter circuit, to have a buffer in between this output and the main amplifier. Yeah, I think that's the main thing that we had to look at here. So plus minus 1 volt peak. So this is the datasheet of the 2N3904. You see there they specify a maximum current, a collector current of 200 milliamps, and they define the gain at 10 milliamps. I did choose 20 milliamps as a collector current to drive it a little harder. And as we already mentioned, we set the output voltage at around 6 volt, maybe a little less, because a VBE is 0.7, and so 6 minus 0.7 divided by 20 milliamps from here gives us this about 220 ohm that I did select for the emitter resistor. Now let's take a look at the datasheet of the 2N2219. We have a maximum voltage collector emitter of 30 volts. That's fine. We have to keep in mind maximum 800 milliamps and maximum power dissipation is 0.8 watt. So I did choose a steady or a DC operating point collector current of 60 milliamps. and I would like to have the main voltage swing across the transformer, and so I did go for 2 volt on the emitter resistor on RE. 2 volt divided by 60 milliamps is about 33 ohms, so I did pick 3 100 ohm resistors in parallel because I didn't have a 33 ohm resistor laying around. And then for the current of the biasing circuitry, I did choose 12 milliamps. That's way above the base current. Typically you choose 10 times the base current as the biasing circuit current. So with 12 milliamps you're way on the best side. You could probably go much lower than that because your base current is much lower than that. Anyway, that gives me about 220 ohm, and because we did choose 2.7 volts there, the other resistor is given as well, the other bias resistor. So now one quick word to this output transformer that we have. I did choose a transformer as the load impedance in the common emitter stage, because I would like to transform the output impedance of the common emitter circuit exactly to 50 ohm, because I need here a 50 ohm match, and matching means if output impedance and input impedance, if those are equally the same, we are at an operating point where we transfer maximum power. The maximum power that you transfer from one 4-pole to the next 4-pole is by when the input and the output impedances are exactly the same. And in high frequency applications, if your impedances don't match, you'll get also reflections. And the last thing that we really want is any signals reflecting back into the mixers, because they get remixed and you get all kind of weird and unfriendly signals because of bad matching and reflections in your circuitry. So keep reflections low, means make sure you have a proper matching. And in an ideal world, the power on the primary side into the transformer is exactly the same power on the output side on the secondary side of the transformer. If you know this basic relationship, then you can calculate the transformers and don't have to remember all these formulas. That's the basic principle of a transformer. And because of that, you can play around with the input impedance and the output impedance. In the end, the power in is the power out. And so you have a relationship by the input impedance that the output impedance of 50 ohm to this 1000 ohm to the primary side is equal to the number of turns on the secondary side to the number of turns on the primary side squared. And in my case, I did choose a 44 microhenry on the collector side of the common emitter transistor, and that's equal to 10 turns with this material. This is FT5043. FT means it is a ferrite core. 50 is the size of the core, and the 43 material defines the permeability of the core material. It has a certain frequency range. It is working in a different frequency range, in a range from 1 to 50 megahertz, so that's just fine for us. But of course, 1 megahertz is already a little bit on the low side. Okay, I guess that's all. If you have a 1000 ohm output impedance here from my amplifier, and I need a 50 ohm. I have a 50 ohm input impedance on this on the amplifier stage. Then I need a transformer that transforms 1000 ohm to 50 ohm, and if I have 10 turns here, that gives me about 2 turns on this side. This is theory. and in the practice you have to tune and tweak your circuitry a little bit. Well, good morning. I give you a quick view into my electronics lab and also in my ham shack. Here you see my minimalistic ham shack, FTDX 10, and I've got some nice power. I'm an expert power amplifier, and there are some cables going out through the window up on the roof. So this is my shack, and this is my lab, and this is all kind of component stuff, and this is the do-it-yourself transceiver I'm working on. And we already went through all kind of videos where we did explain the antenna amplifier and the bandpass filter. We did take a look at the mixers here, the mixer stage, and then the crystal filter. And what's still missing is, of course, the power amplifier. And today we look at the preamplifier to drive the power amplifier. And we have to look at the microphone amplifier and the two-tone generator. And then we have to look, of course, also at the touch display and the digital part of this transceiver. So let's go ahead and take a closer look at this preamplifier here. So we are here on the bench, and the first thing we want to do is measure the quiescent points, the biasing points that we have designed and chosen. We have 12-volt power supply here. We measure now on the base of the 3904. It should be around 5.5, 6 volts. That's over here. That's 5.9 volts. That's right in the center between 0 and 12 volts. And then here on the emitter we should have 0.7 volts less. And that's what we have, 5.2 volts. Can you see it? Okay, 5.2 volts plus 0.7 is 5.9. So it seems to be working, the 3904. Now with the 2219, we should have at the base at around 2.8, 2.5, 2.8 volts. Yeah, that's correct. And then on the emitter, again 0.7 volts less. And this is 2.2. 2.25. So it seems to work, and yeah, it's getting really hot. And this is now the setup to measure the frequency response and the amplification, the performance of this amplifier. That's the preamplifier here. I have my SIG gene over there to generate the input signals, and we then take a look at the scope over here. So on the scope you see the yellow trace, that's the input, and the green trace is the output signal. And on the yellow trace we have a we have a 1 volt peak to peak voltage. VP peak is 1.04 volt. And on the output we have 4.95 volt peak to peak. So we can quickly calculate. It's this 4.95 divided by this 1 volt log and then 20 times. So that's then 13.9, so 14 dB. That's exactly what we have seen before.
in the simulation and calculation. I did choose here a 1 volt peak. We could go all the way up to 2 volts peak. So I increased now the input voltage to 2 volts peak, and you see now an output voltage of 9.5 volt peak. So this is pretty much at the limit with 12 volt power supply of this amplifier, and you see this is not really a sinusoidal function anymore, so we get into the nonlinear range of this amplifier. And of course 2 volts peak input I hardly ever have from my mixer when I'm modulating with SSB. Most of the time I'm gonna be way below these 2 volts, more around 1 volt. If I would increase the power supply voltage, let's say we go up to 15 volts, and you would see the nonlinearity would be reduced by somewhat. It gives a little bit more space on the transfer function of the transistor, but it's not gone. So it's probably safe to stay at 12 volt because the heat dissipation of the transistor is already a lot. And then start reducing again the input voltage, and we go down to 1 volts again. So here we are. Yes, 1 volt input, and gives you about 5 volt output. So far so good. Now let's reduce the frequency, and we go down to 1 megahertz. So we have this 1 volt input again, and we get a 3.65 volts output. So at 1 megahertz it really starts to drop off, as we have seen on the simulation, on the LT Spice simulation. And what is it now? It's 3.65 volts. Let me quickly calculate. This is now 11 dB, an amplification of 11 dB. So we lost 2 dBs at the lower end. Now let's crank up the frequency to 14 megahertz. So here we are now at 14 megahertz. We have this 1 volt peak input, and we have now at the 14 megahertz an output of 5.72 volt, which is it's an amplification of 15 dB. So we have even a 1 dB gain there at the higher side, which surprises me a little bit. I was expecting more, a drop at higher frequencies, but I'm sure the drop will come, maybe not at 14 megahertz, maybe more, even higher up. Let me try. Yeah, here it starts to drop. This is now 14, 15, 16, 17, 18. So right after 14 megahertz it really drops the amplification. You see that here. This is 20 megahertz. We have at 20 megahertz we have a gain of 1. So yeah, the cutoff is right there about at 14, plus minus. All right, that was the frequency response of this amplifier.